once you've got your measurements, but let's say your measurements are on the order of 5 to 10 centimeter thick lifts, or smaller, or whatever. However, you've ended up slicing your model, your core. But that may not be what you want to actually put in the model. So you may potentially either blend, or let's say you've got coarser data, you've got a layer that is 15 centimeters thick, and I have a measurement that represents 3 or 4 centimeters in your core. You may just apply that across a larger interval, because maybe later at a quarter of a meter depth you have another set of measurements. So you don't necessarily always sample every single interval all the way down in your cores. You might, but you might not. It kind of depends upon how much money you want to spend on your SEDFLUME data collection process. But nonetheless, you end up ultimately having to define a set of thicknesses that you want to represent in your actual sediment bed in EFDC and in the SEDZLJ model. So here we have your critical shear stress, the bulk density, the thickness of the layer, and then the grain size distribution. These grain sizes are defined somewhere else, but it's a user-defined grain size distribution. So whatever grain size you think are, that represent the median value of or that best represents that distribution that you have at your site, you'll come up with that grain size distribution, and then you just fill in, this is percentage of the each class for each layer. And then
they measure that during the SEDFLUME test.
Yes, and then they're measuring that during the SEDFLUME session. So this information is all from the data. And then down here, this is also measured. These are your actual measured erosion rates. Again, kind of broken down into this layers, set of layers here. So, and then across the top, you have what we call a shear category. So at 0 shear, we have a very small erosion rate. It's not 0. It can't be 0 because it's being used as a divisor in some places. So EE won't let you use, that's kind of an EE quality control check. If you have a 0 value in any of these fields, it'll notify you and say, it just gives you a warning. It lets you continue with the work you're doing, but it won't let you run the model. If you try to run the model, it'll crash because you're dividing by 0. So you have to have some small number specified, and here it's 10 to the minus 9 centimeters per second. So, and then now the other thing is these are in dynes, centimeters squared. Almost everything, the original EFDC sediment transport model basically used newtons per meter squared or pascals for all of its shear information, although internally to the model, if you take your shear stress and divide it by water density, you end up with units of meters squared per second squared. And that's actually what's generally used in internal. That's the internal model units, because it's density independent shear. So you don't have to worry about water density. This is just straight up shear stress in dynes per centimeter squared. Again, these shear categories here and your grain size categories, these are all defined by you, the user, based on your data. What's the appropriate shear category for your set of shear categories based on your core and your site, defining what these categories all must be. some of the other things later, but that's the kind of, this is what comes out of the SEDFLUME data. So, quoting Earl, if you don't have, you can use literature values and estimate and build up SEDFLUME data, and I think this is, I don't think that this is always necessarily the way to do it. If you have a site that you have a lot at stake on, like a sediment remediation, which are always like in the near billions of dollars, well, you better have some real SEDFLUME data. But if you're doing, you know, a less cost critical project, you know, this approach, you know, could work, where you're just taking other, you know, similar data from other sites and rolling it into yours as an approximation of the data. There's essentially one equation, like we said, in EFDC for all the constituents. Basically following, you've got your terms here where the rate of change of your mass. M here, by the way, and you'll see this, and we'll talk about some documentation here later. I think we have some pretty exciting news for documentation of EFDC that we're releasing. And we'll talk about it at the end here. But anyways, M is essentially, that's your metric associated with the cell size, and the X and the Y, essentially. So this represents the cell area, MX times MY. So that's sometimes represented in the equations in documentation as just M, meaning this cell area. So, you know, then we've got your adduction in the U, the X and the Y, and then your vertical adduction terms. Over here on the right-hand side, you've got your diffusion terms on this side, and then you have a source sink term. So, essentially what we're focusing on, the difference in the SEDZLJ versus the original, and both the sediment transport models versus the your dissolved constituent component, is you have a settling term here. So this is your settling speed of particular classes of sediment, and then so this is changing your overall distribution of your concentration, and then ultimately also as essentially a loss term to the bed down here as it settles out, or a source term if it's eroding into the water column. So options here are the user specified velocities, or EFDC Explorer, as well as EFDC, will allow you to just assign velocities based on your grain size and the density, and grain density of, grain size of your particle. The density, actually that equation should be divided by water. That's the density of the solid. That's your grain specific density. So really what you're looking at, supposed to be here, is the difference between your density between the water and your sediment grain. Just notice that, sorry about that. Anyways, and viscosity. So you get this representative D star, and it goes in the equation. You can calculate here your settling velocity. So that's changed in Van Ryn, using your standard approach here with diameter and viscosities, etc., and these different grain size bins, produces these types of this curve here. So this, we have three curves shown here: Chang, Van Ryn, and Stokes. But Stokes divided by 10, because when you start getting to these larger grain sizes, you can see Stokes starts really significantly over predicting your actual settling velocity. These smaller ones, it's at least kind of in the range, but this is divided by 10. So these are quite high by comparison. But here is the Chang settling velocity in blue, Van Ryn in red above, and this is the discontinuity between some of those breaks in the size classes. So it kind of calculates it slightly differently, but as you can generally see, Van Ryn has slightly higher, albeit, I mean, certainly I'm sure well within the measurement of the uncertainty of the actual environment that it's in. Either one will work, but I think that Chang producing a little bit lower settling velocity for the same size class. So all of that, let's see, what time is it?
9:44.
9:44? Let's go to 10, then we'll cover, let's see, actually.
The question.
Yeah.
So